Welcome to Deep Learning with Flux. This course will build upon the previous course, Fundamentals of Machine Learning, by showing you how Flux provides lots of helpful APIs and frameworks in order for you to define your machine learning toolchain and pipeline in a much easier way. Recall in the last course, we were working with a classification task between images of apples or bananas using a single neuron that we created entirely from scratch. While that's helpful for pedagogical purposes, it's not what you want to be doing over and over and over again. Flux provides the utilities to show you how you can, Flux provides the utilities to enable you to do this in a much more regimented and easy manner. So Flux will make this classification task much simpler. We'll start with the same classification task and then extend that in order to examine both how Flux works at a basic level, but then also extend it to multi-level, multi-layered neural networks of deep learning and so on. So let's get started. This notebook will show you the basics and contrast how Flux works compared to how you did it manually in Fundamentals of Machine Learning. So to get started, we'll use the Flux package as well as some plotting packages for interactive examination of what's going on. And of course, if you don't have those, you can add them using PKG. First off, you'll notice that Flux has a lot of helpful built-in functions. For example, remember how we were continuously implementing and re-implementing the sigmoid function? Flux provides that for us, bound to the sigma variable here. And just as a reminder, you can type that with a backslash and sigma with a tab. And it's defined just as you would expect. And there's even a helpful Wikipedia link here if you want to know more. And of course, you can plot that to see that it is indeed doing what we want with the sigmoid function. Flux also allows us to automatically create neurons and all the supporting architecture that you need in order to work with a neuron. So in the last notebook, we had two inputs, the two mean, I believe it was red and green values of an image, and combine those together to an output, to either output 0 for an apple or 1 for a banana. Well, we can do all the work needed to set up this with the dense function in Flux. So simply by saying a model is a dense function, with two inputs, one output, and the sigmoid activation function. You can, of course, extend this in arbitrary ways with many inputs and, as you'll see later on, many outputs. But for now, let's stick with the two inputs and one output to contrast how that works against what we did in the prior course. Now, remember we had to set up a vector of weights as well as a bias in order to run our neural networks when we manually did that. The model object already has those things for us, named just as you would expect them. So a W has the weights and B has the bias. Now, there are a few things to note here that are different from when we did this by hand. One is our W isn't a vector at all. It's a matrix. It's a 1x2 row vector, and just a matrix with a single row, but that's different than what we had done before, where it was a column vector. The other thing to note here is that it's not just printing out a 1x2 array, but it's a tracked array. And that's extremely important in how Flux does its works, its magic, and we'll see that a little bit later in this notebook. You can see that these types here are indeed tracked arrays, and they're effectively just wrapping a regular array. The model provides a few extra utilities that are extremely helpful. For example, let's say we have a 2-element data point. Let's just use a random 2 elements here, just as an example. You can evaluate the model at that data point to see what the output is. And it's just done by calling the model itself. So that model isn't a function, but it can behave like a function. And so you can call it like a function to see what the output is. And you can actually reason through how this is working, right? Because when we had defined this manually, we took the dot product between our W set vector of biases by our x features and added that to a bias and used the sigma nonlinearity to do that, right? Well, we want to do this with Flux's model. So in order to change that to work with Flux, we just simply, access model. Now it's a capital W because it's a matrix. And because it's a matrix, we don't need to transpose and multiply to do the dot product. We can simply just multiply to do a matrix multiplication and add our bias like this. And again, our bias is tucked away in our model as well. And you can see by doing this manually, we get exactly the same result as we do when we evaluate the model. This is the definition of a dense neuron. So that is what a model provides us. That's going to be very helpful as we go about our task of training this model in order to represent our data. One last thing that's helpful that Flux provides is it also provides a bunch of cost functions or loss functions. And we had manually defined these before too, right? We had often been using the total sum squared error in order to define our loss function. Well, Flux has a mean squared error function, which is effectively the same thing, just normalized by the total number of data points. And you can see that here, defined even using the standard y-hat notation for our estimates. So that is flux.msc. So let's bring that all together and work on looking at how we would train this model given a set of data points. So let's do that with a set of data points that encompasses our apples and bananas. We have them stored in CSV files, actually tab separated files. So we use the tab delimiter in the data folder in this current, in your current directory. So you can load a set of data points for apples and a set of data points for bananas. We're going to additionally specify that there are no missing values. That makes our life a lot easier. Don't need to worry about imputation in this case. And we'll normalize the column names to make them a bit more readable. So those are apples and bananas. And you can see that there are summary statistics for a bunch of images for each of these. So we have 490 images of bananas summarized here with their heights, widths, the mean red, the mean green, and the mean blue values for all of our images. Similarly, if you look at what the apples were here, you can see that we had 492 examples of those and the same 5 columns. So those are our data points. We can hide that for now. We want to extract out just our 2 features that we're interested in. Those are our red and green values. So we create a vector comprehension here that's going to be a vector of vectors, where each element is a vector of its 2 features. So we can do that. And again, we're doing it both for our apples and our bananas. If you just want to look at our apples in this case, you can see we have 492 elements. Remember, 492 images, and each element is a 2-element vector of features. So those are our x's. Now we want to combine them together, right? We don't want to handle our apples and bananas separately. Let's put them together into one vector that just has them stacked one on top of each other. So this is a vertical concatenation. So that way the first group of data points come from our apples. The second group of data points come from our bananas. You can see what that looks like here. So now in total we have 982 elements. The first batch here all come from our apples. The second batch are all our bananas. Same thing. Now we need to create our known labels. So we know the labels of our example data, right? Either it came from an apple or from a banana. So in the cases where it came from an apple, we can fill zeros in that. So the size of our apples array, we just fill zeros in, and the size of our bananas array, we fill ones in. So our y's then end up being a whole bunch of zeros at the beginning, and then a whole bunch of ones at the end. So those are our data. That's what we're going to be using to train our model. So as a reminder, this is our model, 2 inputs, 1 output, the sigmoid activation function. We can evaluate our model at our first data point, right? Now our model is randomly initialized, so this is pretty much gibberish. What we want this to be, of course, is a 0, because our first data point is an apple. And the last data point, we would want to be a 1 because that's a banana. Neither is true at the moment, so we need to train our model. How would we do that? Well, the first thing that we did when we did this manually was we looked at the loss value, right? We constructed the loss at a given data point. So we can look at the loss at the model evaluated at our first label as compared to the label at that value. You can do that at any of our data points or the data set as a whole. But let's just keep looking at this one data point and remember that the other thing that we wanted to do, that we need to do in order to train our model, is to figure out what the gradient at this data point is so that we can walk down the gradient, do gradient descent in order to improve our predictions. So let's look again at what model.w was. Remember, it's a tracked array. Well, what is it tracking? And you can dig into this. I encourage you to look into what this model.w is doing. And one way to do that is just to start looking at its properties. So if you add an extra property accessor dot there and hit tab, you can see that it has 3 fields: data, grad, and a tracker. Well, data, that is just the data itself, right? This is the unwrapped. It's now no longer tracked. It's just our plain old array that we're used to working with. So that's our data. And what's our grad? Well, right now it's zeros. But you can think, look ahead and think like, oh, this might have something to do with gradients. It's the next step, right? Is figuring out the gradients. Well, that's exactly what it is. So all the parameters of the model, both our biases and our weights, have a gradient associated with them. Right now they're set to 0. So how do we figure out what the gradient is at a given evaluation? Well, we have our loss computation. Remember, we computed our loss, and our loss computation is also special. It is also tracked. You can look at what the type of our loss is here, and you'll see that it's a tracked real number. It's a floating point number, but it's a tracked real number that has additional information in it. And what is that additional information? Well, it's all of the operations that were done in order to compute it. So it knows about what we did when we computed this. So it knows where we were and what values were used in the computation here. So that means that if we use our Flux.tracker utilities, we can do this back propagation, which is expressed with just simply a back bang. And it's a bang function because it goes through and it mutates all the things that this loss computation touched that were also tracked. And it mutates them to add information about the gradient at that point. So it's building up this tape of all the operations, and then it's using basic calculus in order to figure out what the gradient is based upon what the operations were that were done at that point. So this is extremely handy. If you'll recall from fundamentals of machine learning, there we did our gradient computation using numerical methods, which were unstable and kind of a pain to set up, and also a little bit slower. This is a great way of doing it and a very common technique to figure out our derivatives and our gradients. So how do we use this gradient information then in order to bring this together? Well, let's grab our loss evaluation here. Let's bring this all together. So we have our loss. We're taking our values, our first x's compared to our first label. We did the back propagation of our loss. And now we need to modify our model parameters based upon those gradients, right? So we want to modify our data, the core data that are tracked W wraps, by subtracting out the model.w.grad, the computed gradient. And of course, we always want to multiply this by some learning rate. Often it's called eta, so let's define an eta learning rate. as just maybe 1/100th. So we modify our model to see what to update based on the gradient. And we do the same thing with our biases, right? And it's exactly the same, only with model.b.grad times our eta. So this is basically one step in a gradient descent algorithm where we find our x's and our y's and we do a back propagation based upon that loss computation and then update our data. So let's do that one. But first, let's see what our current value is, right? So model of x's of 1, that currently gives us 0.45, and it should be 0 because this is an apple. So we can do this, compute the loss, and see what our new evaluation is at our model.x's. And it should be a little bit closer to 0 because we take one small step down our hill in order to improve our results. And indeed, you can see this was 457 thousandths and this one's 456 thousandths. So it's one step closer. Of course, what we really want to do is we want to loop over our entire data step a bunch of times, maybe let's say 1,000 times. We want to pick a random data point to do a stochastic gradient descent. So rand from 1 to length x is here, and we keep our eta value the same. Everything else is the same here, except we pull out our x's and our y's like that, and like this. So we can do this a whole bunch of times and update our model based on that. And you can see now our value at our x's of 1 is very improved. It's very close to 0. And looking at the x's of n, these should be close to 1, and indeed they are. So we have now trained our model based on using Flux's thing. This is effectively implementing stochastic gradient descent again in order to train our model. Of course, you don't want to implement stochastic gradient descent every time you want to do a machine learning task. And of course, Flux makes this a lot easier for you. So Flux has an Sgd Optimizer built in. You can actually ask for help on it. And it just takes parameters and a learning rate, also called eta, and it runs the gradient descent optimizer. Flux also has a training loop, right, where it goes through lots of data points and computes the loss and then runs the optimizer for that. So the optimizer is effectively what updates our parameters in our model. The loss function is what that is totally untrained, and all we need to do is create a loss function, and we're just going to use, just like we did before, the mean squared error between our model evaluated at the x value against its label. The optimizer, what that does is you just take the parameters of the model. Well, what are the parameters of the model? We can look at that, params of our model. That is a 2-element array of basically just our W and our bias. So the params of our model is exactly the same as just saying model.w, model.b, and putting it into a vector like this. That's the same thing. So those are our model parameters. And then all we do is we run train against this. And this is one extra thing that you need to be noted here is that Flux expects the data to be zipped together. So the zipping combines our x's and our y's so that way they're paired. So that way our first element has a pair of our one x data point against its label, the next, and so on and so forth. So they're paired together. So this just runs one training step of our model. And we can visualize this result in order to see what things look like. And you can tell after one training step, it didn't do very well, right? We want the, we're plotting here, these are our x values, or our data points, and the model evaluated around those data points. So you can see down at the bottom left, it's saying, oh, these are probably bananas, ones, and up in the top right, these are probably apples, those are 2. But you can see that's totally wrong, right? The bananas are at the top and the apples are at the bottom here. So there's a lot of training that's needed to go on to improve it. So We can do that just simply by running our training algorithm a lot of times. So for step in, let's do, say, 100 times. Let's train our algorithm and see what happens. Since we initialized with random weights, where we start in this process is always going to be a little bit different. So I'm never quite sure what's going to happen, but here it looks like 100 steps was sufficient in order to train our model. Now you can see our zeros are down where our apples are. The decision point here is somewhere in between, and our ones are our bananas. So we successfully trained this model using Flux. And not only that, but we also found a little bit of insight into how Flux works. So how Flux does its back propagation, how it lays out its data, how it organizes things. And you can see that in the end, all we ended up with was effectively 4 lines of code to define our model, define our loss function, define what optimizer we were going to use. In this case, it was a stochastic gradient descent. That's kind of the basic classic algorithm. And then we trained it. And in fact, we trained it a number of times. But that is machine learning with Flux.